of this one, design principles for power screws, and then after that you have to solve the problem. Okay, so I've already given you the slides. So basically power screws, example is a screw jack. So this is used for lifting a load or for applying strong force. So for example, this is one example of power screw here. So here, if you rotate the screw and if you restrict the rotation of the nut, then what will happen is, as it rotates, it will force the nut. So nut will go up or down. Okay. So you can imagine that you can use this as a force to do something. Okay. So for example, if you have power source on this right side and you turn the screw and you restrict the rotation of the nut so that nut doesn't rotate with the screw, then in that case it will apply some force on the nut and nut will move up or down. Okay. So that's a very, very simple mechanism, okay, but very, very important, because there are a lot of machines which has got this power screw. Okay. So you can see a lot of such equipments. So main application to raise heavy weight to obtain accurate motion in machining operations. For example, lathe machine, if you see in the lathe machine, it has got power screw. So by power screw, the lathe is moving. To clamp a workpiece like in vice, you use this one. And to load a specimen, as example, universal testing machine. So there is a universal testing machine which is used for doing a tensile test or compression test. So that is also based on this screw, power screw. So very, very useful mechanism. Okay. So we will do the design part. That means we will find out how we can decide the nominal diameter, the core diameter, and also the thread. Okay. So pitch and the lead. How we can decide those things, because you cannot just select any dimension. Okay. And in engineering there is something called under design or over design. Okay. You should not under design. What will happen if you under design something? What will happen? Anybody? If you under design something, then what will happen? Why we should not under design?
There won't be enough information.
Sorry?
There won't be enough information for you. There will be a lack of information if you do under design.
No. Under design means something which has not been designed to the required strength, required load it can take. So, for example, you are designing a table to hold a very, very heavy piece of machine. Then you should not be using this table. This table will just crash, right? So in that case, this is under design, because the load is much more than you have designed it for. It's like a very tall building structure. If you are designing, you have to design it differently. So that's under design. And what is over design then? How do you define over design? Somebody should say something. What is over design?
Something which is not of the actual purpose. This will not be used in the actual purpose of something.
Over design means something which you have designed it too much. For example, a table, just now I talked about tables. So a table which is only for to keep the computer and to work, but you have designed its legs and its structure, the frame, so strong that it can take tons of load. Then in that case it is over design. Okay? So you should not under design. Under design means it will fail. So that's ruled out. You should not under design. you should not over design. If you over design, that means it is costing too much for nothing. Okay, you are spending too much. So sometimes people will do this, to make sure that it doesn't fail, just go for over design. So over design is also not good. Okay, but sometimes over design things will fall by itself, okay, because the weight is so much, right? So if you design a bridge which is so heavy because you just didn't want to calculate things, you just you told the person, okay, just make a very, very thick girders and very, very thick beams, then what will happen? The bridge will collapse on its own weight, right? So over design is also not good, under design is also not good. So that's why we study design, so that we design exactly for the need, our need, or maybe taking care of the safety factor. And that's why we have safety factor, so that we take care of the safety part and we design exactly for what it should be. Okay, so that's why we will do this exercise of designing this screw, okay, for whatever load it has to take. Okay? So again, as I said, you should not over design it. So you should not select dimensions which will take this load anyway. If I have got 5 kg to be hold like this, I will just make this beam so thick that it will take care of the 5 kg. But that is wastage of the material and money. So just going through some of the advantages and disadvantages of power screw. So large advantage is large load capacity, compact size. This is very, very important because in many of the engineering applications you need to have compact size, and this power screw provides a very good compact size. Instead of this, if you take any other mechanism, it will take a lot of space. Simple design, all you need is a screw and a nut. Easy manufacturing, large mechanical advantage, high precision. This is also very important. For many high precision machines, power screw is used. Smooth and noiseless motion, low maintenance, less number of parts. So reliability is better, low cost, and self-locking design possible. You can make it self-locking. But disadvantages are poor power efficiency, used mostly for intermittent power transmission. So we do not use for a continuous power transmission mechanism. High friction leads to wear of screw or the nut. Usually nut is made of softer material and wears faster. Okay, so these are disadvantages, but the advantages are quite many, and we do use this power screw. So there are two types of threads. So one is the square one and another is trapezoidal. So today we will do the exercise for square thread. Okay, so I have already gone through this Acme thread and buttress thread, but we will do the calculation for square thread. These two tables, square thread table especially, provides you some possibility of nominal diameter and pitch. So you should select one of these combinations. So for example, you can select 24 nominal diameter and 5 pitch. You should not use 24 and 6 or 24 and 7. So this proportion has to be maintained, and out of this nominal diameter you can select any depending upon your need. So that's what I said, that based on your need about stresses, you have to select one, and if it doesn't satisfy the requirement, then you have to go for one higher, and if you think it is over designed, then you should go for one lower. Okay, so all the optimization has to be done here in the selection. These are how we write the thread. So for example, square 30 cross 6 means nominal diameter 30 and 6 is the pitch. So this gives a drawing of the thread. So P is the pitch, L is the lead. As I said, there are screws with multi pitch or multi lead. So in that case, pitch and lead, there is a relation between pitch and lead. So lead can be 2 times of pitch or 3 times of pitch, and so on. DC is the diameter of the core, and DM is the mean diameter here. So there is a core diameter, nominal diameter, and mean diameter. And these are the relations you can see. And here, important thing is tan alpha. So alpha is the angle which actually determines how much lead is, how much your load is going to be lifted per turn. Okay. So if you turn 1 round, how much you are going up. You know, it's like in a spiral ladder, right? If you go 360 degree, how much did you go up? So that is important. So that is the lead. So if you unwind the thread and you make it a straight line, then it will be like a triangle. Okay? And L is the lead, and pi dm is the mean circumference, and alpha is the angle. Okay? So you can say that tan alpha is equal to L divided by pi dm. Okay? So this equation holds. So that's how this triangle comes. So for every turn, and 1 turn means 360 degree, we travel pi dm and we go up L. So now case 1, torque required to lift the load. So now if there is a load, so the sliding is taking place between the 2 threads. Okay, so this represents that thread here, and this is the lead and alpha. So here if you do the force balance, W is the load. So W is the load that you are going to lift. So you are designing for this W. So W is given. Okay? And so depending upon the friction, you can say mu n is the force in this direction, n is the normal reaction to this one, okay? And P is a imaginary force to balance all this out. So these are the forces at this point, at any point. So we can write those equations. So P is equal to mu n cos alpha plus n sine alpha, and equilibrium of the vertical force gives us W equal to n cos alpha minus mu n sine alpha. So dividing 4 by 5, we get this one, and then finally we get this P is equal to W multiplied by this. So we further simplify the equation, as you can see here, okay? And then finally we get P equal to W tan phi plus alpha. Now the torque MT required to raise the load is given as P is the force that we have to, virtual force that we have to apply, dm divided by 2. Okay, so this is the torque. So that torque we have to apply to turn around the screw and lift the load. Okay, and that can be given as this equation. So this MT is the torque to lift the load, and here you can see the friction is playing its role, tan phi. Okay. Tan phi is the friction, and the angle, the helix angle it is called, alpha is also playing its role. So your design of the screw will depend upon the friction force, friction coefficient, and also the alpha. Okay. Now if you want to lower the load, then same thing, but you have to see the force balance here. In this case, the friction force mu n is in the opposite direction. So you apply P on this direction to balance them out, and then you write these equations which you can go through, and we can get the torque as this equation, by this equation, where tan phi minus alpha comes. So there are 2 situations, case 1 to lift the load and case 2 to lower the load. Our calculation today will be for raising the load. Okay. There is another thing is about self-locking screw. So torque required for lowering the load is given by this one, and when phi is less than alpha, the torque required is negative. That means no torque is required to lower the load. Okay. So as a limiting case, we should have psi is equal to is greater than alpha, so that the screw doesn't go down by itself. You know, it's like if you put the load, the screw will start going down. So that should not happen. It should be self-locking. So that is the condition for self-locking. Mu must be greater than L over pi dm. Another is about efficiency of a square thread. So efficiency of any system is obtained by work output divided by work input. So how much we are getting out of how much we are putting in. So work output is WL divided by P pi dm. So the efficiency will be given by this equation. Okay. Substituting for P from equation 10, we obtain this one. Okay. So this is the efficiency we can obtain for given value of phi and alpha. And we can say, because tan alpha is equal to L over pi dm, we can say mean diameter, the efficiency depends on the mean diameter of the screw, the lead of the screw, and coefficient of friction. So there is a graph here for helix angle against efficiency, and you can see that beyond certain helix angle there is no further improvement in the efficiency. So this helix angle is something around 30 or little bit above 30. Okay. And also the efficiency depends on the coefficient of friction. As you reduce the coefficient of friction, the efficiency goes up. So these are the conclusions from this one. Efficiency of a self-locking screw. So again, you can go through this analysis to see what is the efficiency of the self-locking screw. Now, collar friction. So if there is a collar here, so obviously the collar should not rotate along with your screw here. So there will be friction here. So that friction can also be estimated here. And the torque required for this friction. But by design we can reduce this friction. We can actually, because this is not participating in raising the load. So sometimes they come with a ball bearing, so that the friction is reduced to almost close to zero compared to the friction in the screw. If both torques are to be considered, then the total torque will be mt plus mtc. This is because of the collar. Okay? So that means the friction in the screw is for raising the load, and friction in the collar is basically because the collar has to stay there and there will be some friction. So in that case the efficiency will go down slightly. Now the design of a screw and nut. So basic components are screw, nut, and the frame. So material selection is the first thing we do once we decide to make something. The screw, sufficient strength to withstand stresses due to external load and applied load, possess high wear resistance, must be ductile with good machinability. So the materials are basically plain carbon steel as well as some alloy steel. So for high strength we always go for steel. Nut, soft compared to screw material, so we want the nut to wear out faster than the screw. Okay, because the nut is small, it can be changed more frequently than the whole screw. So the nut is made of softer material, and friction also should be low. So tin bronze or phosphor bronze is used. The frame, high compressive strength, damping and cheap, grey cast iron is used for the frame. So these are the material selection. Now criteria for mechanical design. So first is the strength criteria. So in that case you consider the compressive stress, and you calculate the compressive stress, torsional shear stress in the circular cross section, and what will be the shear stress, okay, because of the torque. And combining them together, you can find out the maximum shear stress by this equation. Okay. So then maximum shear stress must be lower than the possible shear stress, or the the shear stress allowable shear stress. Similarly, shear stress in the screw thread and shear stress in the nut thread also has to be calculated, and then you have to compare it with allowable shear stress. Another criteria is wear criteria. Wear is a function of the bearing pressure. So in this case, the bearing pressure is basically used. So what is the bearing pressure? And the bearing pressure must be lower than this one, because if the bearing pressure is higher than this one, then material will wear out very fast. And there is also buckling criterion, so that the whole, since the screw is a long thing, it can fail by buckling. Buckling, when you press a very long stick, it just buckles in the middle, right? So it should not happen that way. So for that, we have to have this condition, okay, satisfied. So you have to satisfy the strength criteria and the wear criteria and the buckling criteria. Now, once you get the question paper, then step 1 you should do, find out permissible compressive stress and shear stress for the screw and the permissible shear stress for the nut thread material. So these are based on the property, material property already given, right? Then size of the screw, using the equation for allowable compressive stress, find out the size of the screw in terms of DC. Now go to the table 6.1 and select a combination of D and P such that it gives some value of DC. And since there will be shear stress due to the torque, hence we should select one higher value of D. Okay, so whatever value of D you select for compressive stress, you go one level higher, because there will be shear stress as well. So you have to take care of that. Then trial 1, now we should check if the selected value of D and P satisfy the permissible stress condition. Find out the torque, tau and sigma C, and then tau max for the screw. Check tau max with permissible value. If satisfied, then proceed further, or else go back to the table and select a new combination. Let's say the stress that is coming is more than the allowable stress, so that means you have under-designed it, so you go for one higher. Or if it is difference is too much, then you go for one lower. But again, there is a lot of going back and forth here in this case. Step 3 will be length of the nut. Calculate the number of threads Z for the nut. Make it nearest whole number. Calculate the length of the nut with this Z and P, and then you have already selected the screw. Check if this condition is satisfied. If this condition is not satisfied, then you have to change the nut length, either lower or higher. Okay. Because if this condition is not satisfied, then it will buckle. And step 4, now calculate the transverse shear stress for the screw. And transverse shear stress is basically because of the load. The load is being applied on the thread, so the thread is subjected to shear stress. So load divided by the area. And you compare with allowable shear stress. Do the same as above for the nut. So if you do all these things, and if all the conditions are satisfied, then your answer will be the D and P, the nominal diameter and the pitch. Okay. And using pitch